We have a 2-meter long pin-ended column of square cross-section. Okay, so we have here a 2-meter long pin-ended column. So both the ends are hinged. All right. If this is the one end and if this is the second end, both the ends are hinged. If this is the initial column, then after buckling, it will be somewhat like this. All right. So after applying some load, it will buckle somewhat like this. Since it is a pin-ended column, on both the ends I have shown a hinge joint. The cross section is square and made up of wood. So here we are using a wood material. Now assume E as 12 GPa for wood. Alright, so E is equal to 12 GPa, which will be equal to 12 multiplied by 10 to the power 3 MPa for wood. And the allowable stress being limited to 12 megapascal. So sigma allowable, they have given it as 12 megapascals in this material of wood. The allowable stress, they are saying it as 12 megapascals. We need to determine the size of the column to support the following load. So there, they are basically planning to load this column, which is made up of wood and of square cross section, to the following loads, that is 95 kilonewton and 200 kilonewton. The factor of safety to be taken is 3, because since they have given us the allowable stress, therefore we have to consider the factor of safety. Some factor of safety we will have to consider, and the Euler's crippling load for buckling. So we are not supposed to use the Rankine's critical load formula, that is PCR, which we derived just now. They want to basically predict the cross section by only considering the Euler's crippling load for buckling, and the Euler's crippling load for buckling, or the critical load for buckling, PCR, is given as what? It is given as pi square EI divided by L square, right? And what is L? What is L for a column which is pinned at both the ends, or which is hinged at both the ends? This L equivalent for this kind of column is given as L, right? It is nothing but small l itself. So the actual critical load for this column will be pi square EI divided by small l square, because this L, capital L, is the equivalent length for a pin end joint for both the ends which are pin or hinge. This equivalent length turns out to be small l itself. That is the total length of this column, which is, by the way, 2 meters, right? They have given this as 2 meters here. So since why we are using this as a critical load formula? Because they have asked us to use it, right? They have asked us to use only Euler's crippling load for buckling, or Euler's critical load for buckling. Okay, so since this is our expression for the critical load, which are nothing but here the critical loads or the applied loads are 95 and 200 kilonewtons. So for this load we need to actually find the dimensions, right? So let us now consider our case 1, right? Case 1, wherein we have to subject it to a load of 95 kilonewton, which is nothing but around 95 multiplied by 10 to the power 3 newton, right? For this we need to find the dimensions of this square cross section column made up of wood. All right, so what we'll do is, first of all, we need to consider this factor of safety of 3, right? We need to consider here the factor of safety of 3. And how to consider that? The working load will be nothing but it will be equal to the critical load divided by the factor of safety, right? But the critical load in case of this is nothing but it is pi square EI by L square, and the factor of safety is how much? It is 3, right? Factor of safety is 3, because they have asked us to take it as 3. And how much is the working load? It is 95 multiplied by 10 to the power 3, right? So basically we know here everything. Now we know what is the value of E, which is given to us. We know L is 2 meters, so the only unknown is I, and this I will help us to find this dimension, right? If this is a square, if this cross section is a square cross section which is made up of, say, initially we'll assume it to be of dimension A, then how much will be the moment of inertia of this square cross section of dimension A? It will be A multiplied by A cubed by 12, right? So I will be this. So if if I further substitute the value of this I in this expression, what I will get, this will be 95 multiplied by 10 to the power 3 equal to pi square multiplied by E. E is given as how much? It is 12 multiplied by 10 to the power 3 megapascal. So this will be 12 multiplied by 10 to the power 3 multiplied by I. I we can write it as a to the power 4 divided by 12 divided by this 3 and this L. L is 2 meters, right? So I have to multiply it by 10 to the power 3 to convert it into mm, and that will be our L. In fact, this should be L square, if I'm not wrong, right? This should be L square, yes. So this should be also square. So from here now only unknown is A. Now if you solve all this, if you put it in a calci and then calculate all this, you will find the value of A to be, A should be equal to around 103.67 mm. Now from Euler's critical load formula, we are getting this as A to be 103.67 mm. Let us check how much is the dimension if we just test it for a crushing load. How to check for its dimension for a crushing load? We know that the crushing stress sigma C multiplied by A, that is the crushing stress multiplied by area. This should be equal to how much? This should be equal to the applied load, that is 95 kilonewton or 95,000 newton, right? But the crushing stress here or the allowable stress is given as 12 megapascals. So since it is given as 12 megapascals, this will be 12 multiplied by area of the square section is A square. This should be 95000, which will give us this A as what? It will give us this A as 88.98 mm, right? But from crushing load the dimension is less, right? The dimension comes out to be 88.98, but can we construct our column, square column of this dimension 88 of dimension of side 88 mm? No, right? Because if we construct our column of this dimension, it will definitely fail under the bending load or under the crippling load, because there it demands the dimension of 103.67 mm. So therefore our final dimension for this load of 95 kilonewton will be, A will be equal to 103.67 mm. Because if we build a column of this dimension for a load of 95 kilonewton, it will not only take care of this crippling load or the buckling load, but it will also take care, automatically it will take care of the crushing load also. So we have to construct a column of this dimension. Now one may do the same thing for the second load also. One may repeat the same step for the second load also, and then you will get the dimension of A for the second load, that is for 200 kilonewton. It will turn out to be 129.10 mm. Alright, you may try that. You will get a square cross section of this much of dimension. Okay, so this was a very simple problem just to demonstrate how to make use of the Euler's crippling load for buckling. But only thing is, make sure that if you are using the Euler's crippling load for buckling, if it is given in problem, you have to also check what is the dimension for a crushing load, all right? Because as we had discussed just now, it doesn't, this Euler's critical load doesn't take care of the crushing load. So therefore we have to check separately if it whatever dimensions we get, if it fails for the crushing load or no. And then whatever the highest dimension you get, with that we can design our column. Okay, so this was a very simple problem just to demonstrate the use of the Euler's critical load formula. Let us go to the second problem. We need to determine the buckling load for a strut of T section. All right, we have here a T section, and its dimension should be this. I can take it as around 100 mm. All right, thickness we will take it as around 10 mm. Then this distance from here to here, its height basically, height from flange to bottom of the web, it will take it as 80 mm, all right. And then this thickness again we will take it as 10 mm. So we have this T section. The flange width is 100 mm, overall depth is 80 mm, right? Overall depth is 80 mm, and this width is 100 mm. Both the flange and the web or the stem is of thickness 10 mm, which we have taken care of. The strut is 3 meter long, all right? The strut, which we can which as we had discussed in our beginning lectures. The strut also we can treat it with the theories that are developed for column. So we will be using whatever theories we have developed for column. Same theories we will be using for strut. As we had said in our first video, whatever theories that are developed for columns, the same theories will be used for strut. Okay. Now here the strut is of 3 meter long. So basically here the L is 3 meter long, 3 meter long, and is again hinged at both the ends. So that means the equivalent length L will be equal to L itself. So that will be 3 multiplied by 10 to the power 3 mm. So this is what we get, that L will be 3 multiplied by 10 to the power 3 mm. We have got what is L. Alright, the dimensions of this T section is given to us, and we need to find the buckling load. We need to find the buckling load. Now in this problem, nowhere they have mentioned about the crushing stress, right? Nowhere they have mentioned about the crushing stress. Since nowhere they have mentioned about the crushing stress, what we'll assume is this whatever we are designing now, whatever strut we are designing, it is probably it is safe for the crushing stress, and therefore the formula which we'll be again using is only the Euler's critical load formula, PCR, and that will be again equal to pi square EI divided by L square. And then since since this strut is hinged at both the ends, this L turns out to be equal to small l itself, that is the total length, which is 3 meters. Okay, so I hope you all understood why we are not taking the Rankine's formula. That is because here nowhere he is speaking about sigma c, right? Nowhere he is speaking about the sigma c. So we have to again design this using the Euler's critical load formula. Because if we are using the Rankine's formula, we have to have some information about the crushing stress or the crushing load, which is not present here. All right, so we'll go ahead with the Euler's critical load formula. Now here the question will be, now which I to take? There can be I in the x direction, which is Ix. There will be also Iy, right? If I take this as somewhere here as our centroidal point, then in that case, this will be our neutral axis. This will be our neutral axis, right? And similarly here, this will be our neutral axis. So now our question will be which I to take, whether to take I about x axis or whether to take I about y axis. And in case of columns, because it may buckle in either side, right? It may buckle either in this side or it may even buckle along this side. So this T section, let me draw this in a isometric view. So this is a column. It will look somewhat like this, right? And how much is the length? The length is 3 meters. So it will run down to a 3 meter long, all the way 3 meter long column, right? So I'll just abruptly end this here, and then it may now fail when it will be subjected to a load, when it will be subjected to a compressive load. It may either buckle along the x-axis or it may even buckle along the y-axis. So here our question will be, now which I to be considered. So here usually the guideline is we'll have to find Iy as well as we'll have to find Ix, and whichever is less, we have to design this strut for that I. All right, if Iy is less, we will design this for Iy. If Ix is less, we will design it for Ix, because the moment we take care of the lesser value, it will automatically take care of the higher value. So therefore we will have to find both Ix as well as Iy. So if you want to find now what is Ix, you will have to first find what is y bar, right? What is y bar? We very well know by now how to deal with all this, how to find Iy or Ix. So y bar here, this will turn out to be 100 multiplied by 10 multiplied by 5 plus 70 multiplied by 10 multiplied by 35 plus 10 divided by, this will be 100 multiplied by 10 plus 70 multiplied by 10. I will not waste much time in explaining all these things again, because already this has been taken care in very much detail in the properties of area topics, right? So y bar will come out to be 21.47 from the top end. So this will be our y bar from here to here, right? So therefore Ix will be moment of inertia about x-axis. That is, if this is our x axis, which are the horizontal axis passing through the centroid, and if this is our y axis, that is the vertical axis passing through the centroid, then Ix will turn out to be 952,990.2. Again, I am not going into detail how I have got this. You need to refer our earlier videos. Similarly, Iy, that is the moment of inertia about y-axis, it will turn out to be 839166.67 mm to the power 4. And as I had told you earlier, the way we will design this strut is, in order to find the critical load, we will take the least value among both this moment of inertia values, that is Ix and Iy. We will go ahead with this least value, that is this value, alright, because since this is a lesser value. And therefore, the critical load formula, which is nothing but PCR, which is given as pi square, I'm sorry, this should be pi square EI divided by L square, will be taken care as pi square multiplied by E. Now, how much is the value of E? It is 200 GPa. So, in terms of MPa, I have to multiply this by 10 to the power 3 multiplied by I. Value of I will be this, right? So here I will be equal to Iy, which will be nothing but this value. So that will be 839166.67, right? Divided by L. So how much is the length here? Length is 3 meters. So this will be 3 multiplied by 10 to the power 3 square. Now, if one solves everything, if one solves this expression, you will get this PCR, that is the critical load, as 184,049.85 Newton. So this will be PCR will be equal to 184.05 kilo Newton. So this is the critical load which we have found using only the Euler's theory. Now here are two very important points which one needs to remember is that since they didn't mention anything about the crushing stress or crushing load, we didn't make use of the Rankine's formula, because if you remember, the Rankine's formula takes care of both crushing stress as well as the Euler's formula. But since nothing was mentioned about the crushing stress, we didn't take into consideration the Rankine's formula because of no information was available for crushing stress or crushing load. This is the first point you need to remember. The second point is that whenever we will have this kind of sections, whenever we will be having the sections which are not symmetric about both the axes, then in that case, and if the Ix and Iy value both are different, then while designing or while finding the critical load value, we have to take I in such a way that the minimum value of out of Ix and Iy will be our I. So in this case, Iy was the minimum value, therefore we took that value, alright, because it can buckle either this side or it may even buckle this side, right? So in this case, it will, since we took Iy value which is very less, so that means it will buckle, there are chances that it will buckle this side, all right. So therefore we took the Iy value and we found the critical load. Since we designed it for the minimum I, it will definitely take care of this Ix, right? It will definitely take care of this Ix. Let us go to few more problems. Let us try to solve few more problems by taking into consideration the Rankine's formula also. Till now, for these two problems, we had not taken into consideration the Rankine's formula. So in this problem, we shall take into consideration the Rankine's formula also. So we have here a hollow circular shaft of iron whose whose outside diameter is 200 mm and has a thickness of 20 mm. So we have here a hollow shaft made up of a iron, all right, probably cast iron, whose outside diameter, that is this diameter, is given as 200 mm, whereas its thickness from here to here, it is given as 20 mm, all right, is 4.5 meter long. So here L is given as 4.5 meters. In terms of mm, it will be 4.5 multiplied by 10 to the power 3 mm, right? And is fixed at both the ends. All right. Now this column is in such a way that it is fixed at both the ends. All right. It is fixed here at both the ends. At this end also it is fixed. All right. And at this end also it is fixed. And then calculate the safe load by Rankine's formula. We need to calculate now the safe load by Rankine's formula using the factor of safety of 2.5. So we have here a factor of safety which is to be taken as 2.5. Now, he has also asked us to find the ratio of Euler's Rankine's load to Rankine load. It should be Euler's, find the ratio of Euler's load to Rankine load. Other properties like E is given to us. E is 100 GPa, which can be again written as 100 multiplied by 10 to the power 3 MPa, because we prefer everything in terms of mm and megapascals and newtons. All right. Rankine's constant is given to us very well. A is given as 1 divided by 1600 for both pin and case, and this shouldn't be for both pin and case. This should be for a both fixed and case. All right, since this was fixed at both the ends, this will be also fixed ends. Right, this should be also fixed end case. And crushing stress is also given to us. This is all very much required, right? If I want to use the Rankine's formula, I require this crushing stress, which is 550 megapascals. With the help of all of this, we should be able to calculate the critical load by using both Euler's as well as Rankine, and finally we will find the ratio. All right, now here look at this is a hollow circular cross section. So here there will be nothing called as Ix or Iy, both will be same, right? Because since it is a circular, it is made up of a circular cross section. It is in the direction of x or in the direction of y. The moment of inertia will be same, right? The moment of inertia will be same. So we can just calculate here I, and I for a circular cross section, it is nothing but it is pi d raised to 4 by 64. Yes, I is pi d raised to 4 by 64, where d is what? I mean, since this is hollow cross section, I'm sorry, this should be pi d raised to 4 by 64 minus pi d raised to 4 by 64, right? The formula for I for a hollow cross section is pi divided by 64, capital D raised to 4 minus small d raised to 4. Yes. Now, how to find here the small d? Small d is nothing but this. This is our small d, right? This is our small d. So what do we see here is that 2 times thickness plus small d should be equal to capital D. So therefore, what will be small d? Small d will be capital D minus 2 times thickness. So therefore, this small d will be 200 minus 40, which will be nothing but 160, because 2 times thickness will be 40, right? 2 multiplied by 20 will be 40. So this small d will be 160. So therefore, if I substitute this here now, which is nothing but pi divided by 64, this should be 200 square minus 160 square. I mean 200 to the power 4 minus 160 to the power 4. This will be equal to 463,699.08 mm to the power 4. This is the value of I. Now let us talk about effective length. Effective length L will be what? It will be, since this is the fixed end case, both the ends are fixed, and therefore if you remember, if both the ends are fixed, it will be half of the actual length. The effective length turns out to be half of the actual length. Please go through the previous video, all right, for this. Since both the ends are fixed, the effective length L will be half of the actual length. So this will be half of how much? It will be half of how much is the actual length? The actual length is given as 4.5 meters. So half of actual length will be 4.5 multiplied by 10 to the power 3 mm. So this value will turn out to be 2250 mm. Okay. Once we get this, since we need to find the ratio of Euler's to the Rankine load, first let us calculate what will be the critical load from the Rankine's formula. So I mean from the Euler's formula. Euler's critical load formula is given as what? PCR from Euler. It is given as pi square EI divided by L square. Okay, so this will be pi square multiplied by E is given as 100 GPa, so 100 multiplied by 10 to the power 3 MPa multiplied by I value, we just now found it to be this 463,699.08 divided by L square. The effective length turned out to be 2250 mm. So therefore, this critical load from Euler's formula, PCR from Euler's formula, we will get here this value as 9400, 2.3 Newton. Alright, so from Euler's critical load formula, we got this as our value. Let us now try to find from Rankine's critical load formula. From Rankine's critical load formula, we get this PR. We know that it is sigma CA divided by 1 plus A times L divided by K the whole square. But here what is K? If you remember, K is the radius of gyration, right? K is the radius of gyration. So how to find this value of K? The value of K can be given as what? The radius of gyration value of K square, in fact, is nothing but I divided by A, right? I divided by A. So therefore, I can find this K as root of I divided by A. I value we already know what it is. It is 463,69908, and divided by what is the area of this hollow cross section? The area of this hollow cross section is pi by 4 capital D square minus small d square, right? So this will be pi by 4 multiplied by 200 square minus 160 square. So this area of this rectangular cross section will turn out to be 11309.73 mm square. So which will substitute it here now? 11309.73, 11309 So this K value will turn out to be 64.03 mm. Okay, so once we get this value of K, I will get this value of PR, that is from Rankine's formula. I will get this critical load as sigma C is given to us. How much is sigma C? It is 550 megapascals, right? So just substitute this as 550 megapascals. Area we found just now, it is coming to be 11309.734, all right, 0.734 divided by, we have here 1 plus A is given to us. The value of A is given to us as 1 divided by 1600. So A is 1 divided by 1600 times L by K whole square. Length is known to us, that which is the equivalent length, which is 2250 divided by K we found just now, 64.03 whole square. So finally we'll get this critical load here from Rankine's formula. We'll get this critical load as 3510907.3 Newton. And then they had asked us to calculate the ratio also, right? So ratio of this Euler's critical load to the Rankine's critical load, which is nothing but PCR from Euler to this Rankine, to this Rankine, PCR from Rankine. All right. So this is how much? This will be 9040052.3 divided by 3510907.3. So this ratio will approximately, it will turn out to be 2.575. And then we had to also calculate the safe load, right? We had to calculate the safe load by Rankine's formula. So critical load from Rankine's formula has turned out to be this. Yes, so here just we need to make use of the Rankine's, I mean the factor of safety. So safe load, so here the safe load from Rankine's formula will be what? P Rankine, that is the load from the Rankine's formula, critical load divided by factor of safety. So this will be 3510907.3 divided by factor of safety. Here they had asked us to take the factor of safety as 2.5. So just divide this by 2.5 and finally we will get this safe load from the Rankine's formula as 1404.363 kilonewton. So this is how we can make use of the Rankine's critical load formula in order to predict the critical load. Okay, so let us solve one last problem under this topic, and that is the critical load by Rankine's formula and Euler's formula. So here again we need to determine the section of a cast iron hollow cylinder column which is 3 meter long. So here again length is given to us as 3 meter with both ends firmly built in. So which basically tells us again that both the ends are fixed. Since both the ends are fixed, the actual length will be half of, I mean the equivalent length will be half of the actual length, will be 1.5 meters, which I can write it as 1500 mm, right? I just have to multiply it by 10 to the power 3. Okay, so this is given to us. Since it is firmly built, therefore the equivalent length turns out to be half of the actual length, right? And then if it carries a actual load of 800 kilonewton, so it is carrying the load of how much? 800 kilonewton, which I can further write it as 800 newton. Okay, the ratio of internal to external diameter is 5 by 8. So what it is saying is capital D by small d is 5 divided by 8. So here this is the external dia, this is the internal dia. So this is capital D, and from here to here it is small d. So the ratio of capital D by small d is 5 by 8, which will be required later on. Factor of safety he is asking us to consider as 4. We need to take the factor of safety as 4. The crushing stress is given to us. The sigma C is given to us, which is 550 megapascals. And the Rankine's constant for a both end hinge case. Again, they have given it as both end hinge, but we will take it for this end case, that is the firmly built or the fixed end case, which is nothing but A is equal to 1 divided by 1600. Okay, for all this we need to determine the section. So determine the section means basically we need to find the value of d and value of small d. So here first of all what we can do is we can say that from this ratio capital D is 5 by 8 times small d. So everywhere wherever we find the capital D, we will substitute it as 5 by 8 times small d, so that our unknown remains only in terms of this small d everywhere. Okay, so for example, if I want to calculate now I, the moment of inertia here is for the hollow circular cross section is always pi by 64 outer d square minus inner d square, right, which will be equal to pi by 64 times okay, here I did one small mistake. The ratio, this is the ratio of internal to the external dia, right? So this should be actually, truly speaking, this should be small d divided by capital D, because it is the ratio of internal dia to the external dia, which is 5 by 8, which is less than 1. This doesn't make any sense, right? The capital dia cannot be less than the small dia, or the outer dia cannot be less than the inner dia. So this inner diameter, it will turn out to be 5 by 8 times the capital dia. Okay, so this is what we get from here. So therefore what I can do here is I can keep this d square as it is, and internal diameter I can what I can do is I can replace it as 5 by 8 times the capital D whole square. So everything I will get it, everything I will, everywhere I'll get this expression in terms of the outer diameters. Okay. Similarly, what I can do, I can calculate the area. The area of the circle is given as pi by 4, outer d square minus inner d square. So this will become pi by 4. This should be 4. This should be 4, right? This should be 4. Yes, this should be 4. So this will be capital D square minus small d square is 5 by 8 times capital D square. Alright, and on similar basis I can find the radius of gyration K, which is nothing but capital I divided by area, which will be nothing but I have to divide this term with this term, right? So this will be 1 by 16. Pi and pi will get cancelled out. 4 by 64 will be 1 by 16, and this will be capital D square plus small d square. Alright, it will be capital D square plus small d square. You may try out this. You can write it in terms of d square minus small d square times d square plus small d square, and here numerator will have this term. One term will cancel out with this, so finally it will remain with this expression. So I can further substitute this small d as what? 5 by 8 times 5 by 8 times capital D the whole square. So if I just simplify this term now, this should be plus, and further if I simplify this, I will get this as K is equal to 0.295 approximately times capital D, outer D. All right, so we have got this term K, and then we'll straight away now go to the Euler's critical load formula. For that we also require L by K ratio, right? So let us find that L by K ratio here itself. L we got it as 1500 divided by K we have got it as 0.295 times outer D. Okay, and then working load is given as how much? The working load P is given as 800 kilonewton, right? The working load is given as 800 kilonewton, which should be 800 multiplied by 10 to the power 3 newton, in fact. Yes, so this is what is given to us. And then the critical load is nothing but, we know it is working load times factor of safety, because what is working load? Working load is given as critical load. Working load is given as the critical load, or the the critical load divided by factor of safety. Yes, so therefore the factor of critical load can be found out as critical load, that is PR, P suffix R from Rankine formula, PCR I can write, and here I can write R. This will be equal to what? Working load, that is 800 kilonewton multiplied by the factor of safety, which is 4, right? I have to just multiply this 800 multiplied by factor of safety. I will get this as critical load, and that will be equal to 3200 kilonewton, which will be again equal to 3200 multiplied by 10 to the power 3 newton. So now we have almost all the quantities which are required in our Rankine's formula. So if I go for this Rankine's formula now, that is PCR, which is given as sigma Ca, it is a crushing stress multiplied by area divided by 1 plus Rankine's constant times L by K the whole square. Alright, so here now we have to substitute all of these quantities, that is sigma CR. PCR we know it is 3200 multiplied by 10 to the power 3 equal to sigma C is given to us, and that is sigma C, that is the crushing stress, is given to us as 550 megapascals. Let us substitute this as 550 megapascals. Area we have to write it in terms of this capital D, it is pi by 4. Pi by 4 times what this will be, capital D square minus pi by 8 times the capital D square, right, divided by now 1 plus the small a is given to us, that is 1 divided by 1600, which we had noted down here. I will have to write it here again, 1 divided by 1600. L by K ratio, we know what is L by K ratio, right? We already wrote it here. So this is 0 divided by 0.295 times D. Alright, L by K it is square, so this is square term. Okay, so from here we will get this D, in terms of equation, and that equation will be D square plus 16,179.775 is equal to 8.2259 multiplied by 10 to the power minus 5 times d to the power 4. We will get this equation. Once we solve this everything, we will end up getting this equation. Now from here we will get this ds, it will be around 146.16 mm. You may try to solve this. In fact, I think you will get two values of D. The negative value of D you can neglect and only concentrate on the positive value of D, because diameters cannot be minus. So the only considering that the positive value, one will get this capital D as this. So therefore what will be small d? Small d is pi by 8 times capital D. Therefore we will get this small d as 91.35 mm. So this is how you can make use of the Rankine's critical load formula in order to find the dimensions, or in order to design the columns for different types of loadings with the different types of boundary conditions.